Thank you for the introduction. Yeah, so I'm Laura, and I'll be talking about my joint work with Robert Huang and John Preskill. Okay, to give some motivation for this problem, as you all probably know, finding ground states is a really fundamental problem in physics and has a lot of applications in, say, like material science and also chemistry. But despite recent improvements on trying to find classical algorithms to solve this problem, classical computers still really struggle to solve this problem in the fully general case. So for example, you may have heard of like the DMRG algorithm, which works really well in one dimension, but for higher dimensions, it becomes very difficult and it's less efficient there. So then this raises the question, can classical machine learning algorithms efficiently predict ground states after learning from some amount of data? So does this training data, which are like examples given to the algorithm, somehow help to make this problem easier? And at last year's QIP, Robert presented this result, which says that there does indeed exist a machine learning model that achieves this average prediction error of at most epsilon for predicting this ground state property, which I have here is trace-o rho of x, and I'll talk about that some more later. And yeah, so this algorithm only uses n to the order 1 over epsilon amount of training data. And that's really good because if you consider some constant fixed epsilon, then this is only polynomial in the system size. But one thing that you might notice is that for a really small epsilon, then this polynomial is really, really big. And so for using machine learning in practical cases, this might not be so good. And this raises the central question of my work, which is, can we do better than this n to the order 1 over epsilon in amount of training data? And my work answers this in the affirmative, and in fact, you can get an exponential improvement when you consider a constant fixed epsilon. So what my main result says is that the amount of training data scales as logarithmic in n, where n is the system size, and for the scaling in epsilon, it's 2 to the polylog 1 over epsilon. And again, this is for the average prediction error in predicting a ground state property. So yeah, so one thing that I want to note is that for again, for the fixed constant epsilon, then this is an exponential improvement over the previous algorithm, which was polynomial in n, but here it's only logarithmic in n. And in addition, if you consider the scaling in epsilon, then previously, the previous algorithm scaled exponentially in 1 over epsilon, but here it's only quasi-polynomial. And in order to overcome a sample complexity lower bound that was proved in Robert and collaborators' previous work, we did need to add an additional assumption on the structure of the Hamiltonian, but it was a fairly mild assumption, which I'll talk about later. And even with this assumption, we still have computational hardness. So this is a simple corollary of the previous work. And all that it says is that assuming some standard complexity theoretic assumptions, then even if you try to predict just 2D Hamiltonians, then no classical algorithm that does not learn from data can do this for even just one body observables with a constant average prediction error in polynomial time. And meanwhile, in our work, despite this computational hardness for algorithms that do not learn from data, we can, our result applies for just any Hamiltonian of constant dimension and for any few body observable that can be written as a sum of geometrically local observables. Okay, so that was kind of the motivation, and now I'll talk more specifically about what the actual problem statement is. And then I'll go into the actual algorithm that we use, and finally state like the main result and the ideas behind the proof. And at the end, then I'll go over briefly some of the numerical experiments that we conducted. Okay, so first for this problem statement. Here we consider a Hamiltonian H that is parameterized by some m-dimensional vector x with entries between -1 and 1. And moreover, we say that h of x can be written as a sum of few body interaction terms. So here on the slide, this is just that h of x is equal to the sum over the sum of the hj. And so here, all of the assumptions are the same as in the previous paper, but the additional assumption that we make here has to do with this xj. So what this denotes is that each local term in this sum depends only on a constant subset of the parameter vector. So each hj doesn't depend on all of the parameters at once, but only a constant subset of them. So this is the additional assumption that we make in order to get this improvement. And so overall, the problem that we want to solve is that if we had some ML algorithm, we train it on the data, then if we were to give it some parameters describing a Hamiltonian, then the classical ML algorithm will do some prediction, and it will give us a classical representation of the ground state, or in particular, for our case, a ground state property. And how I define a ground state property is by this trace O rho of x that I've mentioned a bit before, where rho of x is the ground state of the Hamiltonian h of x, and O is an observable that can be written as a sum of geometrically local observables. And we also assert that this observable has a spectral norm bounded by 1. Okay, so I just stated the goal up again here. And since this is a machine learning algorithm, we need to feed it some examples, some training data. And this training data is given in the following form. So it's given as these pairs, XL and YL, where XL is some parameter vector, this m-dimensional parameter vector, and it's sampled actually from any arbitrary distribution D. And the other element in the pair is YL, which is the label corresponding to XL, and this approximates the ground state property. And the way that we get this training data can either be through quantum experiments or classical simulations. And so in a quantum experiment, you might imagine synthesizing the ground state in the lab and performing some measurements. Or you could just spend some computational time to classically simulate it. Okay, so now I will talk some about the algorithm. So one really key part of the ML algorithm that we use is this feature mapping. So we take the parameter space, this m-dimensional parameter vector, and we map it into a higher dimensional feature space. And that feature vector I'll call phi of x. And the way that we do that is the following. So here again, I'm considering the parameters describing the Hamiltonian. And what I said before, this key assumption that we make is that each local term of the Hamiltonian, the HJs, they each depend on this constant subset of parameters. So you can imagine that a local term in the Hamiltonian just, for each local term, only this constant region of parameters really matters when doing our prediction. And so in particular here, then I'll highlight each of these little constant regions of parameters. And the way we make the feature vector is then, for each of these regions individually, we make this small vector here. And what we do then is we concatenate all of these smaller vectors together into one large one, and that is phi of x. Okay, so once again, the feature mapping is just taking the parameter space and mapping it to a higher dimensional space. And the reason why we do that is because in this higher dimensional space, then the ground state property that we have is actually can be predicted as a very simple form. In fact, it's just a linear function. So here our hypothesis function is this vector of coefficients W dotted with the feature vector phi of x. And so we can use some standard machine learning theory, in particular L1 regularized regression or the lasso algorithm, over the feature space in order to predict functions of this form. Okay, and as a summary for what this algorithm does, here again, after training the machine learning algorithm on some training data, then if we feed it some parameters describing the Hamiltonian, we make this feature vector, we run lasso, and then we output a ground state property. Okay, so now I'll talk a bit more about the main result as well as some of the proof ideas. So first, there's this theorem again, so I have it just on the screen again. And remember, the important part here is this training data size, which is much reduced from what it was previously. And one thing that I would also like to note is this fact that the training data can be sampled from any arbitrary distribution D, which is taken there. And this is important because it's another improvement over the previous algorithm, because previously, the training data could only actually be sampled from a uniform distribution. So this is another improvement on the previous work. And again, we can compare this to the scaling for the previous work, which is n to the order 1 over epsilon. And moreover, both of these algorithms require computational time that scales in order the system size times the training data size. And so by reducing the sample complexity, we also automatically get an improvement on the computational time. So this scales as n log n in system size. Okay, so now I'll talk a little bit about some of the ideas behind the proof for how we went about proving that theorem. So the first key part is finding a simpler form for this ground state property that we want to predict. And this is where we pretty heavily use the additional assumption on the structure of the Hamiltonian. So we can consider writing our observable O that we care about predicting the ground state property for in the Pauli basis. And then what we can do is just suppose we consider only one term in the sum, so some alpha p, and care about predicting the ground state property for that specific term. And so that's just what I have on the screen is this alpha p trace p rho of x. And what I have here is that there is a region of parameters for each Pauli p. So what I mean by this is, consider this figure again. So what I was talking about before was that each local term, because it only depends on a constant subset of the parameters, then we only need to consider a certain, constant size region of parameters for each local term in the Hamiltonian. But the way that we can relate this to the Pauli p is that if we consider some Pauli that is close by to a local term, so it acts on qubits that are nearby to this local term, then we can also just consider, again, that same region of parameters for the Pauli instead. And so when we do our feature mapping, remember that we made these small vectors. And then what we can say is that actually, for each ground state property, so the alpha p trace p rho of x, that actually can be approximated as a linear function of these smaller feature vectors that we made. And then so adding all of the alpha p terms together to make O, it corresponds to just combining all of the vectors and combining all of the regions together. And so what we get then is that the entire feature vector phi of x is related linearly to the ground state property trace O rho of x. So this is overall just kind of a sketch of what the ideas behind the proof were, but for a full technical description, please refer to the paper. So yeah, this is the theorem that I was stating from this intuitive description. So trace O rho of x is approximated by a linear function of phi of x. In particular, the linear function has coefficients given by this vector w prime. So what this also tells us is that the machine learning algorithm that we proposed, which also predicts linear functions over the feature space, has the high enough representation power to, in order to cover the ground state property that we care about predicting. Okay, and another thing that we really need is this norm inequality. So in particular, the efficiency of L1 regularized regression, which is a key part of our ML algorithm, depends greatly on the L1 norm of the coefficient vector W. And what I mean by this is that when you're computing the sample complexity, you need to choose some hyperparameter B, which corresponds to a constraint under which you optimize over. And in particular, that constraint is just that the one norm of the coefficient vector W must be bounded above by this B. And how do we choose B? Well, we can choose it then by just looking at our W prime from the previous slide and seeing if we can find a one norm bound on W prime to educate our choice of B. And so what this then guarantees is that when we when we run the machine learning algorithm using lasso, then the W star, say, the coefficient vector found by lasso, will yield a smaller training error as well. So the W star might not necessarily be the W prime that we had on the previous slide, but nonetheless, the coefficient vector found by lasso will still yield a small training error. So in order to find the one norm bound of W prime, what we need is this norm inequality. And what it says is, again, writing O in the Pauli basis, then we say that the one norm bound on the Pauli coefficients of O are bounded above by a constant times the spectral norm of O. And here, this is why we require the spectral norm of O to be bounded above by 1. So then this one norm of the Pauli coefficients is just bounded above by a constant. And for those of you who maybe saw Robert's talk on Monday about learning arbitrary quantum processes, this might look very similar to his quantum Bonin-Blust-Hill inequality. And this is indeed a special case of that inequality, but in our paper, we prove it using a very different proof technique. Okay. And so now let's just put everything together and to prove the prediction error bound. So previously in the slide where I was talking about the simpler form for the ground state property, I showed that trace O rho of x can be approximated as a linear function over the feature space. And this simpler form of the ground state property guarantees the existence of some hypothesis function that has a low training error. And in order to get the prediction error, we need to choose this hyperparameter b, again, such that the one norm of w prime is bounded above by b. And so when we use lasso subject to this constraint, then some standard learning theory, like the textbook I cited here, just gives out the sample complexity upper bound. Yeah, and just plugging, that's just a result of like, yeah, plugging everything in, and then you can just solve for the sample complexity, what it should be. Okay, so again, yeah, this is the theorem that I just proved. Okay, so finally, I will talk about some of the numerical experiments that we conducted. And here, we consider the 2D random Heisenberg model. And so, just for those of you who may not be familiar, here the sum is over pairs of qubits, I and j, and the qubits are on this sort of grid. And moreover, this jij here are coupling parameters for each pair of qubits. And for our case, then the parameter vector x, which parameterizes the Hamiltonian h of x, is simply given by a vector consisting of just all of these jij. And so what I have here on in the two figures, here I plot the average prediction error versus the training set size. And this blue line here is the algorithm from this work that we implemented. And the gray lines, all three of them, are what was in previous work, the best known algorithms. And what we see here is that in this work, the algorithm, as training set size increases, then the prediction error drops at a much higher rate. And this reflects the improved sample complexity scaling in epsilon. And moreover, on the other part of this slide, then I have a nice visualization which reflects our intuition about how this ML algorithm works. So I was kind of saying how the algorithm should work by only focusing on this certain region of parameters. And indeed, that is what this reflects. So here, the thickness and the darkness of each of these lines in between different qubits represents how much that certain coupling parameter was used in the ML algorithm, like how highly it was weighted. And so here we can see that if we're considering trying to predict, oh, here we're predicting two-body correlation functions, I forgot to mention. So when we're predicting a two-body correlation function for the qubits 6 and 11, then as we would expect, then the coupling parameter that was most used in the ML algorithm is the one between qubits 6 and 11. So this does really well reflect what our intuition about the ML algorithm and using only a constant region of parameters. Okay, and I'll conclude. So here, the main takeaway is that we can prove rigorous guarantees for classical machine learning algorithms that show that they can predict ground state properties with much less data than was previously known. And we have this exponential improvement in system size when considering a constant error epsilon. And this is important because most of the time, if you're trying to use this machine learning in practice, then if you want to feed it more training data, it's often hard to come across. Like, yeah, you have to run these classical simulations, which would take a long time, or run quantum experiments, which, yeah, could be hard in the lab. And so this raises the hope that ML algorithms can be used for practical problems, just by showing that you can use a smaller amount of data. And finally, I have some open questions. So one is, can quantum ML algorithms predict ground state properties even better? So our result for classical machine learning algorithms seems like pretty optimal, at least in system size. It's only logarithmic in n. But then there raises the question of, yeah, can quantum algorithms perform even better, especially maybe for this scaling in 1/epsilon? And to get like a kind of separation between quantum and classical machine learning. And another open question that we have is, can ML learn to predict other physical properties? So for example, like low energy states or low energy state properties instead of just ground states that were considered in this work. And yeah, that's it for my talk.
All right, questions. Let me try to get there. There you go.
Thank you for the great talk. I don't get it. What is your training data in this case? And
so the training data is, this pair. So it's like the XL is some parameter, just like an m-dimensional vector with entries between -1 and 1. That parameter is some Hamiltonian. And the second entry in the pair is this YL. So this is just some number that approximates your ground state property.
yeah, and for which task do you use it, and does it generalize well?
So we use it for the task of predicting these ground state properties. That's like trace O rho of x, where rho of x is the ground state of h of x, and O is the is an observable that can be written as a sum of geometrically local observables. And so even when trained on this training data, then it still generalizes well to things outside of the training set because of the prediction error bound. That's somewhere in the slides. Yeah.
So thanks for the great talk. I suppose a somewhat natural question would be how you see the prospects for extending these results to observables and Hamiltonians that aren't completely geometrically local, maybe that follow, say, a power law interaction like you might see in a chemistry system.
Yeah, I think if I recall correctly, I think along the path in doing this problem, I think we didn't need a geometrically local observable O for, I think, to get like a almost like, I want to say n log n, but I'm not exactly positive on this, I forget. But I think there we didn't need a O to be geometrically local as like an intermediate result. But then in order to get this logarithmic scaling, we found it a bit hard to get rid of that assumption.
Okay, thanks.
Thanks for the talk. I think this is really cool work. So actually, piggybacking on that a little bit, I think he might have been asking about the geometric locality of the Hamiltonian.
Oh.
And if that's not what he was asking, then I will ask it. And then I also had a second question, which is that do you think how important is the ground state part of this work? Like, with these kind of results and techniques, do you think they would carry over to predicting properties of thermal states as well?
Yeah, I'm not too certain about removing the Hamiltonian geometrically local assumption. I guess I haven't thought about it too much, but for predicting like thermal states or something, that's still open. I don't think that there's I don't think that the result would at least immediately non-trivially or trivially generalize to that case.
Yeah, cool, thank you.
Any other question? Well, I think let's get it easier and then. Let's go on. And I mean, okay. Both have time to ask.
Okay, perfect. Thank you. Great talk. My question is, I might have just missed this, but what motivated the choice of lasso regression over, say, like polynomial regression? And if it's what I was assuming should be just because you wanted that L1 regularization, why L1 over like L2 or like other regression techniques that do a mix of both?
Yeah, I guess so. Actually, so in the when we were working on this, then the first result that we actually proved was this simpler form for the ground state property. And I guess because it's like a linear function, we just immediately thought of lasso. And then I think around the same time, Robert and collaborators were also thinking of a norm inequality, like the quantum Bohn-Blust-Hill inequality. And so it seems pretty natural to fit both of those together. To use lasso.
Okay, thank you.
I'm going to take this opportunity to shamelessly advertise our paper about a similar work, but for thermal states that came out last week. I thought I'd just pick up on that. Thanks.
Last question. Here. There's one here.
Hi, thanks for the great talk. Can you go back to where you construct the feature mapping vector
or I
thing?
guess this is the same figure.
Yeah, I don't know if I missed this, but can you explain how exactly you picked those short vectors and stack them together? What is happening in the conversion from that first hexagonal lattice thing to the final vector?
Yeah, so it gets a little technical. That's why I didn't really specify it. It's actually like an indicator function. Yeah, maybe we can talk about it offline. But yeah, it's like it requires a bunch of like weird little definitions.
Okay, but the fact that you're picking those particular short vectors, does that somehow guarantee that you will have this decomposition onto the Pauli's? Is that where that decomposition comes from?
Yeah, yeah, yeah.
Okay.
The structure of these these little vectors really plays a big part in
Okay, all right, thanks.
Thank you. All right, so I guess there are many more questions. Let's have them offline. Let's thank Laura again.